Alright guys, welcome to another video in trigonometry. And this video I'm going to be working out odd problems from 5.2 verifying trigonometric identities. So let's go ahead and dive in. Alright, so number one, the problem is secant squared theta minus 1 times cosine squared theta equals sine squared theta. So my objective in all of these problems is to verify that everything on the left equals what's on the right. And so I'm taking a look at what's on the left here. And I see here first, right off the bat, I see a secant squared theta minus 1. And this, whenever I see a something squared minus a 1 or 1 plus something squared, that's usually a tell sign of a Pythagorean identity. So if I look at my Pythagorean identities, I have secant squared theta, and that looks like it would equal, and it's minus 1. So what that is, so I have tangent squared theta plus 1 equals secant squared theta, and that's one of the identities. This is just simply modified where they subtracted the 1 to both sides, and you ended up with tangent squared theta equals secant squared minus 1, secant squared theta minus 1. And so you see that this equals this, so then I can now replace secant squared theta with minus 1 with tangent squared theta. Alright, so let's clean this up a little bit. So let me rewrite this. This is tangent squared theta times cosine squared theta. And so the next thing I want to do, I know that tangent squared theta is a quotient identity. So what I can do with this also equals is sine squared theta over cosine squared theta times cosine squared theta. And now I can see here that I can cancel out my cosine squared thetas. All right, I can multiply them out or divide them out. And that leaves me with a sine squared theta, which is what I had originally up there. So I've just verified that they do equal each other. All right, so let's look at number 3. Number 3 reads sine theta minus sine theta times cosine squared theta, and I want to verify that that equals sine cubed theta. So as I'm looking at the term on the left, I'm noticing here that I have a common factor there. I have a sine. So I can actually factor this out. I can factor sine theta out. Sine theta will be 1 minus cosine squared theta. And there again, there I have a something squared with a 1. I have a 1 minus squared cosine squared theta. So that's one of my Pythagorean identities. If I look at sine squared theta plus cosine squared theta, and that equals 1. So what they've essentially done is that they've subtracted the cosine squared theta to both sides, giving you sine squared theta equals 1 minus cosine squared theta. So then I can replace this with sine squared theta. So let's go ahead and do that. So what I'm left with is sine theta times sine squared theta. And so then when I multiply this out, I end up with sine cubed theta. And there we go. I've just verified both sides. All right, so let's jump over to number 5 now. Number 5 reads cotangent squared theta times cosecant squared theta minus cotangent squared theta. And I want to verify that this equals cotangent to the 4th theta. So I'm looking at the left, and similar to number 3, actually, I can actually factor out a cotangent squared theta there. So let me go ahead and do that and clean this up. So I have a cotangent squared theta times a cosecant squared theta minus 1. this is a recurrent pattern here. I see a squared with a -1. That again is a Pythagorean identity. That cosecant squared theta, cosecant squared -1, that is a cotangent squared theta. Okay, and now I can see here that I can multiply this out. I multiply these two terms, and I end up adding my exponents, and that leaves me with cotangent to the 4th power theta, which is what I have here. All right. Well, let's work on 7 now. 7 is secant theta over sine theta minus sine theta divided by cosine theta. And I want to verify that this equals cotangent theta. Well, what can I do on the left side here? Two things stick out. Number one is I have a secant theta, and I know that's a reciprocal identity, but I can change that later. The other thing here is I have two terms with different denominators, so I can't put this together. So what I want to do is I want to give a common denominator, and so to do that I need to multiply the two terms by the other. So that means I multiply the numerator by cosine theta also, and on this right hand term I multiply by sine theta, which means I also multiply this term by sine theta. And simplifying this out, I end up with cosine theta times secant theta over cosine theta sine theta. Now again, this is all over cosine theta sine theta, because that was the reason to do this, so that I can get one single denominator. So then minus, and this term is sine theta times sine theta, that's sine squared theta. Now, I mentioned before, focusing here on the left side here, that this secant theta is a reciprocal identity. So that secant theta is actually 1 over cosine. So let me put that there. So that's 1 over cosine theta. Interesting. So now I'm noticing here that let me write this so that I can maybe, so it's cosine theta times 1 over cosine theta. And as you can see here, I hope that's obvious that I can cross these out, and I end up with just 1 over 1, which is 1. And I'm kind of starting to see where this is going, because it's 1 minus sine squared theta. And I hope that right there, that tells you that I'm looking at, again, a Pythagorean identity, over cosine theta sine theta. So 1 minus sine squared theta, that equals cosine squared theta. Cosine squared theta is the same thing as cosine theta times cosine theta. And so I can divide out a cosine, and that leaves me with cosine theta over sine theta, which in fact is the reciprocal property of cotangent theta. All right, so far it's been working out pretty well. Let's jump over to number 9.